How do systems make decisions without a single central controller? Agent-based computing approaches that question through autonomous entities that perceive, decide, and act. You will see how agents reason, interact, adapt, and handle uncertainty in complex environments. This unit gives a broad introduction to the expanding field of agent-based computing. It covers individual intelligent agents and their interactions in a multi-agent environment. It also highlights rational decision-making under uncertainty, negotiation, cooperation, competition in computational markets, and practical work with a trading agent in Python. These agents are autonomous, interactive, and adaptive entities that operate in environments and interact with each other to achieve specific goals. Agent-based computing is a computational paradigm inspired by agents. Their interactions can also produce emergent behavior at the system level. Agents are self-contained entities that perceive their environment, make decisions, and take actions. Their main characteristics are autonomy, social ability, reactivity, and proactiveness. In practice, that means they can operate independently, interact with others, respond to change, and take initiative toward goals. In many systems, multiple agents coexist in what is called a multi-agent system. These systems are shaped by decentralization, emergence, and both cooperation and competition. There is no central controller. So wider behavior arises through the interactions of independent agents. The structure of an agent depends on its architecture. Reactive agents follow simple stimulus-response mechanisms. Deliberative agents use more complex reasoning with planning and goal setting, and hybrid agents combine both approaches. Each architecture supports a different balance between speed and depth of reasoning. Key traits shape effective agent behavior. Agents operate in environments with important properties. These include accessibility, which concerns how much the agent knows, determinism, which concerns predictability, dynamics, which concerns how quickly conditions change, and whether the environment is discrete or continuous. These features shape how agents can act effectively. Communication is central in multi-agent systems. Through communication, agents negotiate to resolve conflicts or align goals, coordinate actions for efficient task completion, and share knowledge to improve collective performance. Communication can also follow protocols such as the Foundation for Intelligent Physical Agents standard. Agents often need to adapt in dynamic environments. Reinforcement learning helps them discover effective behavior through trial and error. Evolutionary algorithms support adaptation across generations, and machine learning integration brings methods such as neural networks into decision-making. These capabilities strengthen flexibility over time. Agent-based computing is used in simulation, distributed systems, and artificial intelligence for autonomous decision-making in areas such as robotics and virtual assistants. At the same time, autonomy raises concerns about accountability, transparency, and security. These practical issues matter alongside technical design. Agent-based computing emerged to address modern computational challenges such as scalability, adaptability, and efficient resource management. It is especially useful for complex problem-solving in dynamic and decentralized settings. It also supports distributed decision-making, where traditional centralized systems struggle with scale and fault tolerance. The paradigm also offers flexibility by distributing tasks among agents and allowing them to adapt to environmental change. Another motivation is emergent behavior, where interaction can solve problems more effectively than a predefined top-down approach. It also bridges fields such as artificial intelligence, economics, and biology. In finance, agents support automated trading, risk assessment, and portfolio management. In healthcare, they support patient monitoring, telemedicine, personalized treatment plans, and drug discovery research through multi-agent simulation. These examples show how autonomous and adaptive behavior can be applied to specialized, real-world tasks. In logistics, agents help optimize supply chains, automate warehouses, and manage transportation through dynamic routing and scheduling. In urban planning, they model traffic and energy use for smart city simulation. In electronic commerce, they personalize shopping through recommendation systems based on user preferences and behavior. Reasoning models explain how intelligent agents perceive, process, and act on information. Intelligent agents are autonomous computational entities that make decisions and perform actions to achieve goals. Their defining traits remain autonomy, reactivity, proactivity, and social ability, which connect reasoning to behavior. Proactivity advances goals, social ability, and reason. Reactive agents respond to current inputs without memory. Deliberative agents use symbolic reasoning and planning. Hybrid agents combine both, and learning agents improve through experience and feedback. These types show different ways intelligence can be organized. Symbolic reasoning uses explicit knowledge representations and logical inference. Knowledge is expressed through symbols such as rules or ontologies, and decisions are made through logical reasoning or planning. This makes decision-making transparent and suitable for structured environments, but it can be computationally expensive and less adaptable in dynamic settings. Reactive reasoning avoids complex symbolic computation and focuses on immediate responses to stimuli. It does not rely on explicit world representation or long-term planning, which makes it simple and efficient in fast-changing environments. Its weakness is limited problem-solving in complex scenarios that require foresight. Practical reasoning combines deliberation and reactivity. It supports long-term planning through symbolic mechanisms while preserving low-level responsiveness to environmental change. Compared with symbolic and reactive approaches, it offers a balance of flexibility and efficiency, though it brings higher design and implementation complexity. Correct. Rational decision-making helps agents evaluate options, make logical choices, and pursue objectives effectively. In symbolic reasoning, it supports rule-based deduction. In reactive reasoning, it appears through predefined action rules. And in practical reasoning, it links goal formation with adaptive execution. Its key benefits include optimization, predictability, and scalability. Complex problems often involve incomplete knowledge, stochastic conditions, and dynamic change, so agents must act under uncertainty. Probability theory helps represent uncertainty and update beliefs, while decision theory balances risks and rewards. Common tools include decision trees, Bayesian networks, and Markov decision processes, each with strengths and computational trade-offs. 0, 2, 0, 3, 0, 4, 0, 5. Agent-based computing brings together autonomous agents, multi-agent interaction, and different reasoning models to address complex problems. You have seen why it matters, how agents communicate and adapt, and how rational decision-making supports action under uncertainty. Its strength lies in balancing decentralization, flexibility, and practical problem-solving.